Sample problem 3.3. Determine the ACI design moment capacity Vmn of the beam shown in the figure if Fc prime is 4,000 psi and Fy is 60,000 psi. This is the beam. We have here a beam which is 18 inches in depth, or total depth. We have effective depth of 15 inches. We have width of 12 inches. And we have 3 pieces of number 11 bars, equivalent to 4.68 square inches of area. So the first step is to check the steel percentage. The actual steel percentage or steel ratio should be less than or equal to the maximum and should be greater than or equal to the minimum. Okay? If it goes beyond the maximum, it will be compression controlled, and if it goes below the minimum, it will not be permitted by the code. So, first, we calculate for the steel ratio actual. Now, this is actual. So, AS over BD, AS is given to be 4.68, and B and D are also given. So, we get this value, 0.026. Now, 0.026 is greater than the minimum. Okay? Now, how did we solve for the minimum? Let me use the tabulated solution. We have here table A.7. Our concrete is 4,000 psi. So, we look at this column. And our Fy is 60,000 psi or grade 60. So, we look at this row. For the minimum, here we have minimum row for flexure. We simply look at this value. So, this is the value for the minimum, 0.003. So, right here. So, our actual is greater than the minimum. So, it passed the minimum criteria. How about for the maximum? To determine the maximum value of the steel ratio, we look at this table again. The maximum value happens when the tension in steel is 0.005. Okay? Below that, it will not anymore be tension controlled. But above that, it will still be tension controlled. So, what is the value? The value is 0.0181. That is your maximum. So, 0.0181. However, the computed is 0.026. And the maximum is 0.0181. So, this is clearly greater than the maximum. So, this criteria is not permitted. Okay? So, the section now is brittle and not ductile. That's why here in the book, there is a conclusion that the section is not ductile and may not be used as per ACI section 10.3.5 because it will now be compression controlled, and when a beam is compression controlled, it will not show warnings, and once the ultimate stress is reached, it will just simply burst out and collapse, and that is not permitted by the code because that's not a sound design practice. Okay? Now anyway, we can still compute for the tension in steel just to verify if it is really tension controlled or compression controlled. So we can compute the actual value of A. We know C is equal to T by equilibrium. and C is 0.85 FC prime AB, and T is AS FY. So we can solve for A. A is AS FY over 0.85 FC prime AB. So this is this formula. And plugging in all the given values, we can compute for the value of A to be equal to 6.88 inches. Then for beta 1, we can use a formula, but we can also directly conclude that for 4,000 PSI concrete, beta 1 is 0.85. In the previous problem, I have illustrated that beta 1 can be computed using the formula given in the code. But anyway, for 4,000 PSI, it will be 0. No, the rest of the formula will be 0. So it will be still 0.85. So calculating for C, we can get A over beta 1. So your C is 8.09. And illustrating the strain in concrete and steel, this one is always 0.003, and the strain in steel is unknown. This is question mark. And we were able to solve for the C, and C is 8.09, and we have our D here. D is 15 inches. So we can compute now for our ET. Okay, by the way, this one is 15 minus 8.09. So using ratio and proportion, ET over 15 minus 8.09, using this small triangle here, and we can compare it to this triangle above. So we have 0.003 over 8.09. One equation, one unknown, we can solve for the strain in steel, or ET. Okay, and this has the value of 0.00256, and this one is lesser than 0.004. So therefore, this is clearly compression controlled. Okay, so that is how to solve this problem. We cannot calculate for the capacity VMN because this section is not permitted, may not be used by ACI, because if you use this section and during failure conditions, it will directly crumble down and collapse. Unlike the tension control system or tension control design, wherein it will still show warnings such as deflection, cracking, and vibration. And by that, you can see that the section is safer because the occupants of the building will have some time to evacuate the building because the symptoms are showing. Whereas if the design is compression controlled, when failure happens, the building will just collapse, and then all the occupants will not be able to evacuate. Okay? So that is how to solve this problem.